The history of the theory of plate tectonics. Think about a time before seafloor maps and satellite photos of Earth, even before accurate global land maps. The idea that Earth's outer layer is made of moving plates was not widely accepted until the 1960s. The theory of plate tectonics was probably not included in your grandparents' science textbooks. The theory is built on centuries of data and scientific development. Geologic puzzles. The origins of the theory go back to the first world maps in the late 1500s. These maps included most of Earth. After seeing the shapes of Africa and South America, some people wondered if the two continents were once connected. But how could that have happened? It took 300 years for scientists to come up with some ideas for how continents move. As explorers traveled to the far reaches of Earth, they asked, how did fossils of sea creatures get on top of tall mountains? Is there a relationship between volcanoes and earthquakes? Were the continents once close together, making one big landform? Explaining the puzzle. There were two main explanations for the mountaintop marine fossils. Some believed that global flooding raised the sea level above the highest peaks of the world, but otherwise, Earth's land had never changed. Others observed earthquakes and volcanic activity. They reasoned that processes inside Earth changed the surface, creating new hills and mountains. James Hutton, 1726 to 1797, a Scottish geologist, supported this second explanation. He observed that streams carried sediments away from his farm. So why had erosion not made the world into a perfectly round sphere? He decided that forces lifting sections of Earth's surface must balance out erosion. Hutton's theory required large amounts of heat energy from inside Earth and extremely long periods of time. These were brilliant new ideas about Earth's history, but Hutton was a poor writer. Even the brightest scientific minds could not understand his written explanations. After Hutton died, a close friend rewrote his book about geology. Eventually, scientists accepted Hutton's ideas of a changing planet, but understanding the evidence for plate tectonics was a long way off. Putting the pieces together. Putting the pieces together. The puzzle-like shapes of the continents intrigued Alfred Wegener, 1880 to 1930, a German meteorologist. He was also interested in odd connections among fossils. For example, he found fossils of animals that once lived in tropical climates in areas that now have cold climates. He observed that the same plants and animals appeared as fossils in rocks of the same period on different sides of the ocean. The fossils included a freshwater reptile that was like a small crocodile found in Brazil and South Africa. Can you imagine an entire community of reptiles traveling from Africa to South America? Neither could Wegener. Instead, he proposed a world where all the continents were connected as one huge continent. He called it Pangaea. He wrote of Pangaea as a land where flora and fauna were able to mingle together before they were split apart. In the early 1900s, he published his ideas of drifting continents, a new way of viewing Earth's history. But at the time, most scientists believed the continents were anchored in place. The continents might move up and down, but they certainly did not drift around the planet. Resistance to continental drift. Scientists dismissed Wegener's ideas as physically impossible. In fact, Wegener could not explain what forces had moved large masses of solid rock over such great distances. How could it have happened? Wegener fought for his ideas of moving continents and a more dynamic planet until his death in 1930. Scientists found it hard to ignore the fossil evidence for Wegener's theory. To get around this problem, geologists imagined land bridges crossing the ocean. Fossils of an ancient horse were found in France and Florida. So a land bridge was drawn across the Atlantic Ocean. A lost continent was an attempt to explain connections that spanned the Indian Ocean. These land bridges disappeared when technology allowed us to map the seafloor. The missing pieces. In the 16th century, sailors used long ropes to measure the depth of the ocean. They found out that the seafloor is not as flat as people thought. Knowledge of the topography of the seafloor increased with the development of modern tools. In 1853, U.S. Navy Lieutenant Matthew Maury, 1806 to 1873, published the first ocean bottom chart. It showed evidence of underwater mountains in the central Atlantic Ocean. Survey ships laying the transatlantic telegraph cable confirmed Maury's findings. The first sonar systems were developed during World War I, 1914 to 1918, to help locate German submarines. These systems recorded the time it took for sound to travel from the ship to the sea floor and back again. The ocean depth was calculated from these times. The data collected from this early sonar confirmed the existence of the Mid-Atlantic Ridge. Sonar can also measure the thickness of sediments, an important tool in the study of the seafloor. In 1947, seismologists on the U.S. research ship Atlantis measured the sediment layer in the Atlantic. Scientists had believed that the ocean was at least 4 billion years old. If it was that old, the sediment layer on the ocean bottom should have become very thick. But evidence from sonar readings showed that the layer was relatively thin. Why was that? Seafloor spreading. Harry Hammond Hess, 1906 to 1969, was the geologist who finally came up with evidence that supported Wegener's theory of drifting continents. During World War II, 1939 to 1945, Hess was captain of a transport ship equipped with the newest form of sonar. He decided to use the equipment to gather data all the time. He noticed that the sediment layer was thinnest near the mid-ocean ridge. It got thicker as he traveled away from the ridge. The sediments nearest the ridge had been deposited over less time than those farther from it. From this evidence, Hess and other scientists inferred that the crust nearer to the ridge was younger. This difference in age suggests that the Atlantic seafloor is spreading. It is pushing Africa and South America apart by about 5 centimeters cm a year. Today, we combine satellite images of underwater mountains with earthquake and volcano data to study the processes that shape Earth. These data are evidence that Earth's crust is composed of solid tectonic plates. They float on the fluid portion of the mantle. This evidence strongly supports the modern theory of moving crustal plates, called plate tectonics. It took courage and conviction for scientists like Wegener and Hess to defend and promote their unconventional ideas. Their new ideas changed the way everyone thinks about Earth.